As someone who always enjoyed the pursuit of math, I always felt dishonest using a formula or identity that I had not derived myself. Now, this works for math enthusiastic students, but as I highlighted in the first video, proper mathematical thinking and independence can only be obtained through seeing how it works for yourself. This video will be broken down into two parts. First, the proof of the quadratic formula, and then a quick rant about formulas in math and how it hurts the subject. To begin, understanding how we can solve degree 1 or linear polynomials can show us what we cannot do. When given the polynomial mx plus b equals 0, so the standard line equation, the solution for x can be found by undoing the addition of b through subtraction and then undoing the multiplication of m by division. This gives the linear formula of x equals minus b divided by m. Important to note is that this can always isolate for a variable x when all like terms have been grouped together. Looking at the quadratic, it stands as a problem with three terms: an x squared term, an x term, and a constant term. There are some special quadratics that aren't as difficult to solve for x squared at least. If we had a quadratic with no x term, we can solve for x squared using our linear equation and then add a new operation of the square root to finally give the value of x. Now, to solve any given quadratic, all we need to do is eliminate the x term, complete the square. At this point, most people are familiar with the idea of completing the square, but if you aren't, here's briefly what happens. If we had a square that were the sum of x and h for the side length, you can clearly see with this geometric analogy that x plus h squared is x squared as the larger square, 2xh for both smaller rectangles, and h squared for the smaller square. If we had the quadratic ax squared plus bx plus c, then we could factor out the a term for the first two terms to get a times x squared plus b over ax plus c. Now, we just have to add a term inside so that all of the x terms can be under one square as given by the previous result. In this case, the term we have to add is half of the middle term squared to go from the 2h to h squared. 2h over 2 is h, then square that, that's h squared, in our completed square. And on the outside of the brackets, just subtract a times this term. Now we have this polynomial, a times x squared plus b over ax plus b squared over 4a squared plus c minus b squared over 4a. This can now be written as one of the linear-like terms we examined earlier using the completed square, giving us a times x plus b over 2a, all squared, plus c minus b squared over 4a. To reveal the quadratic formula, all we have to do now is the same process we used for linear solutions. Subtract the constants from each side and bring it into one fraction to give a times x plus b over 2a squared equals b squared minus 4ac over 4a. Now, divide by a to obtain x plus b over 2a squared equals b squared minus 4ac divided by 4a squared. And then square root, remembering positive or negative, to further get x plus b over 2a equals plus or minus square root b squared minus 4ac all divided by 2a. And then finally, subtracting b over 2a from each side will finally get us the familiar x equals minus b plus or minus the square root of b squared minus 4ac over 2a. Now that the proof is complete, it gives the room needed to discuss why it is important that we derived it. The first is understanding. Deriving the quadratic formula can give students a chance to see why the plus and minus is necessary and where the discriminant comes from. The plus and minus clearly shown as we have the result of something equaling a square, and when we square root that, it could have been the minus version, because negative times negative is positive, or it could have been the positive version, and students can see that now. And where the discriminant comes from, they can see that square root term right there decides where the zeros are. It also shows students why all quadratics are solvable and demonstrates the usefulness of completing the square. For all formulas, understanding how it came to be can usually reveal important details about the formula and its restrictions and implications. Also, providing proofs such as this can lead to mathematical curiosity. Most people probably didn't even realize it while watching, but there was a very fundamental question posed. And that was, how do we know that this equation is solvable, and how can we solve it in general, as well as the assertion that we can solve all linear binomials. Both of these questions are what gave rise to entire fields of algebra with deep results. A similar extension that can be driven by curiosity is if you could express a quadratic as a linear equation to solve, then can you express a cubic as a linear equation? As a quadratic equation? Can they be solved in some other unknown way? These are all very good questions to ask, with quite ingenious answers that I encourage any ambitious student to attempt and then learn the proofs. When students only work with the formula at hand, it loses all of this value and is usually given out of context anyway. Students learn to see math as a plug-and-chug subject and are removed from believing that they can be good at math because they see these formulas and are turned off by how to tackle the problems surrounding them. When you have proven a formula you are using, you carry with it the confidence of why everything works the way it does, and it produces an almost mystical feel-good sensation of accomplishment and understanding. Next episode, we'll take a look at a particular motivation for quadratics through a weird lens for math, physics, and in particular, the kinematic equations. Next episode, we'll show how to apply mathematical ideas of proof to axioms that are more specific than the generalizations of math, and how to get these deep results elsewhere. Until next time, keep on learning.